All right, so now that we understand what the copper losses are and what the leakage losses are, let's talk about the how do we enter them into Pscad. As you can see over here, this right here, maybe I can quickly erase this. This right here is where we add the leakage reactance, and this is where we add the copper losses. So this is the one that in red at the bottom, and this right here is associated with the yellow. Now keep one thing in mind: this is reactance per unit, and this is losses per unit. So those are two different things, even though they're per unit, but they're asking for slightly different thing. This is asking for the actual reactance per unit, and this is actually asking for the losses, whether it be in kilowatts divided by the MVA of the rating. So, but before we get into that, let's quickly talk about how do you even extract these values? Where do these values come from? And generally, what would happen is that the manufacturers of these transformers will perform something called a short circuit test, also called sometimes a full load test. Okay, and what's done essentially in that test is is that they will basically apply, they'll put the voltage source here on the primary side, or maybe on a high voltage side. And what they'll do is they'll put a watt meter. Okay, so I'm just gonna kind of like, maybe draw this first like this, like a watt meter, and then they will put an ammeter like this in series with this whole transformer, right? And I drew this bigger just because the watt meter, it's only really measuring real power. Okay, it's just only measuring real power, but in reality, inside of it, it's got one coil which is in series with the circuit, then it's got which is measuring the current, and there's got another coil which is actually in parallel, so it may have another line coming through and connecting. So you may see a setup like this, but don't get too confused about the setup. Really, the main thing is that this meter right here, it just needs one cable in series with the circuit, and the other cable might be coming out and connecting to the neutral. But all it's really doing is just measuring real power. Okay, and we got an ammeter as well, which is giving us the ammeter reading, and then we of course got the voltage source, but we can control this voltage source from, let's say, 0 to 100%, right? So this, if this transformer is 230 kV, the 100%, if we set this voltage source at 100%, it would apply 230 kV, but that's not what's applied in the short circuit case. So let me tell you what we do. So essentially, in a short circuit, another thing that's done is why it's called short circuit is that the secondary side would actually, or maybe the terminals of the transformer, they will be short circuited together just like that, right? Now, of course, there's no impedance on this side over here. So as you're gonna increase the voltage from let's say 0% or zero to towards the 100%, there will be a lot more current, because what we have figured is that if let's say a 100 MVA transformer, we can get how much, we can find out the rated current that we would see in a primary if all 100 MVA is being pushed through across this transformer. How we could do that? We can easily figure that out by, let's say, we could do, uh, I rated on primary side. On primary side is equal to 100 MVA divided by root 3 times a 230 kV is equal to 251 amps roughly. Okay, and that again is the rated current on this side. So what would be done here? They basically, what they'll do is they will start raising the voltage from on the primary side, or high voltage side, from zero, and you will start, let's say, you apply, let's say, a 5% voltage. Okay, let's say the 5% of 230 kV is about, one is about 100 and or 11.5 kV. Okay, so they'll apply 11.5 kV, and they will try to measure the current. Hey, what's my current over here at that point, right? So let's assume that the current at that point is about, let's say, I would assume, let's say, 120. Let's just make up a number, 120 amps. Now, let's assume then what you do is, because 120 amps is still not 251, so you can keep increasing, and they'll go to a certain amount of percentage. So generally, let's say about 10% of the voltage, which is, let's say in this case, is 23 kV, and they start to read 251 amps. Then they go like, okay, well, now we no longer need to stop. We no longer need to increase the voltage. We are now reading 251 in this primary loop. That means at the 10% of the voltage applied, right? So this is how they would come up with the ZPU out of this, right? So out of this particular test, we're about to get two things. We're about to get the copper losses right here, and we're about to get the reactance value, right? So copper losses was easy because copper losses were simply, we got a watt meter, and once we apply a certain voltage, let's say in this case a 10% of the primary voltage, uh, that gives us 251 amps. So at that test, what we're noticing is what we're recording is the real power losses in that watt meter. Okay, so let's assume that meter says 100 kilowatts is what it's reading. Okay, right? And so we got that right in our factory acceptance test or in the manufacturer report, but over here we still haven't received our ZPU. So if you do a quick math, right? So if we know that ZPU is equal to voltage per unit divided by I per unit, right? And in this case over here, what do we know? The circuit is very simple. If I skip all of this stuff here, what we really have at this level is that I've got a 23 kV source like that, right? And and what we're doing is we got the current of 251 amps, right? And all I'm really trying to do is find out this Z per unit, right? I mean, if you think about it, so it's really 20. So Z voltage per unit divided by I per unit can give me a Z per unit. So what is my voltage per unit in this circuit or in this test setup? All I have is 23 kV, so then that means voltage per unit is voltage real divided by the base voltage, which is 230. So 23 divided by 230 is 10% of that, so 0.10. But what about I per unit? So I per unit, already we talked about this. I rated is equal to 251. So again, it's basically I per unit is equal to I real divided by I rated. But our test setup was so that we will stop at the rated test, right? So our real in our test is equal to what? 251 amps divided by, again, the base value. The base value is already 251. So once you cancel the two out, you get a 1 at the bottom, and then over at the top you got you got basically um, 0 0.10. So this is why sometimes it's confusing that the Z, you may see a Z is equal to 10%. Don't worry too much about this percentage sign, just drop that entirely. In my head, when I think about Z equal 10%, I just divide in my head by 100, that's what the percentage sign represents, and just get a 0.10, and that's what your Z is equal to. It's just that the way the math works out, that 10, what they're referring to is that, hey, at the 10% of the primary, I got my rated current, but if you do the math as well, the Z per unit will also be 0.10, and then once you know the per unit value, you can always multiply it by the Z base, and you can actually find the real ohms as well if you need to, but we don't really need that. So coming back again, what do we enter in Pscad? So let's assume, well, we've got two main things here. So we've got, let's say, one thing is this guy right there from our factory, from our FAT will give us that, or FAT short circuit test will give us that. And the second thing is, let's say, is giving us the 100 kilowatts. So what do? We still have one missing piece here. Keep in mind that this is asking for a leakage reactance, right? So we don't have a leakage reactance just yet. We have the Z per unit, right, which incorporates the copper as well as leakage. So how can we isolate the leakage only so we can put that value in there? So what can we do? How can we do that? So we already know the real losses. So what we could do is the copper losses. So power, or basically losses that we got over there, divided by S is equal to R per unit, right? So if you do that 100 kilowatts divided by 100 MVA, you will get 0.001, right? So I have 1, 2, 3, 6. Uh, so 100. Yeah, so 1, 2, 3, 0.001, 0.01 per unit, right? So now what do we have here? We do know that Z per unit is equal to, what is that equal to? Or square is equal to X per unit square plus R per unit square. So we have got the R now, we have got the Z from there. So all we have to do is 0.10 square equals to X per unit square plus 0.001 square. And then once you solve the equation, you will get X per unit is equal to 0.099. And that's then the value that you would, this is then the value is that you would put right in here. So you would put 0.099, and in the copper losses right there, you would be putting again not 100 kilowatts because per unit value, you would just divide that over the 100 MVA, and then that would give you 0.001, and that's what you would put in this field here. So the summary of what we talked about over here really boils down to the short circuit test. It's also called full load test, which gives us the Z per unit in percentage and copper losses in kilowatts. For Pscad purposes, Pscad copper losses, what we need to enter right over there, and those losses are just simply take your kilowatts or copper losses from the FAT, take that kilowatt number and divide it over the MVA base of the transformer, and that's what you would enter in Pscad. And for the positive sequence leakage reactance, all what we have to do is we've got to take the Z per unit, again, take the Z per unit percentage divided by 100, take a square of that minus the copper losses that they provided you, let's say in kilowatts, divided over the MVA, take a square of that, and then take a square root, and then that will give you an X per unit, which is the leakage leakage reactance per unit, because this is effectively equal to R per unit. So I hope that clarifies some of the mystery around what needs to go into these two values. In the next video, we're going to cover some of the other losses that we see in the transformer.